We begin this lecture by continuing doing some examples from from the previous lecture. So remember that last time I introduced two notions: pointwise convergence and a uniform convergence of sequences of functions. We say that the sequence of functions converges pointwise if whenever we fix an x in a domain of fn of x and then let n go to infinity, then the sequence of numbers fn of x goes to a limit f of x. And the uniform convergence was different in the sense that it was related to us defining a distance between two functions. So a sequence of functions converged uniformly to another function if the supremum of a difference over all x's in the domain of fn of x minus f of x was tending to 0 as n goes to infinity. So this is what I want to discuss for these examples. So let's look at the example A first. So A, for the pointwise convergence, we're going to choose any x in the domain. Domain is whole positive x. So I'm going to choose any x greater than 0 and consider the sequence fn of x equal to x plus 1 over n squared. So then if I take a limit of a sequence like this, so x is a constant here, n goes to infinity, and then it doesn't take a long time to figure out by using properties of limits that this limit must be equal to x squared. So then the conclusion is that fn of x converges to f of x equal to x squared pointwise on the interval from 0 to infinity, right? Because for each individual x, fn converges to f of x. Actually, we can probably state this slightly better by rewriting the statement in the following way. I don't want to emphasize fixed x. I'm just saying that because fn of a fixed x converges to f of a fixed x, I'm saying then that the function fn as an object converges to the function f pointwise on the interval from 0 to infinity, where f of x is as indicated, right? So f of x is equal to x squared, and we're looking at this function when x are positive. All right, so then the next question is the same convergence uniform. And that we can decide by computing the distance between fn and f, and we define the distance again as a supremum when x is in the domain, so x is greater than 0, of fn of x minus f of x. So it should be the supremum when x is positive of x plus 1 over n quantity squared minus x squared, right? Because those are my fn of x and f of x. And this can be simplified slightly. By the way, because x plus 1 over n squared is always bigger than x squared, then I can drop absolute values here. And then I can use some algebra to rewrite this thing as 1 over n times 2x plus 1 over n, right? Because a squared minus b squared is a plus b times a minus b. Okay, so, and what is this supremum when x is greater than 0, right? So in this case, n is fixed, right? And I'm looking for the distance between the function fn and f for a fixed n. So what is the supremum of 1 over n times 2x plus 1 over n when x is positive? The supremum certainly is infinity. And infinity clearly doesn't go to 0 when n goes to infinity. Right? So therefore, our convergence is not uniform. Because basically, if I look at the graphs of x plus 1 over n squared and x squared on the interval from 0 to infinity, then the fact that this distance is getting bigger and bigger as x gets bigger just means that the parabola x plus 1 over n squared eventually is going to be arbitrarily higher up than the parabola x squared for a fixed n. So therefore the distance is infinity. So somewhere sufficiently far away from 0, even if n is very small, x plus 1 over n squared is going to be much bigger than x squared. Okay, let's do b. And in fact, because we're dealing with basically a very similar example, I'm just going to copy so that I don't need to rewrite all of this. So for part B, the only difference is that I'm considering the sequence of function on a different domain. Now, domain is x is between 0 and 10. Okay, so choose any x between 0 and 10. And let's see if that does change anything. Okay, if I pick any x between 0 and 10, right, still fixed x. So then for a fixed x, this function still, when n goes to infinity, so fn of x, not this function, but this sequence of numbers, fn of x for a fixed x, it still goes to x squared, nothing changed. So that means that we still can conclude that pointwise, on the interval from 0 to 10, fn of x still converges to fn still converges to f. Right? Because when I say pointwise, I'm fixing x, then it doesn't matter which interval of x I took, because every time I'm looking at one specific x, right? So because I had convergence convergence of fn to f on the interval from 0 to infinity, then I should have pointwise convergence on any subinterval. Okay, so now what about the uniform convergence? Well, we'll do exactly the same thing, except now the distance is going to be the supremum over all x that belong to the interval from 0 to 10, right? So that's the only thing that we would need to change. Instead of taking supremum over x greater than 0, now we're assuming that x is between 0 and 10. So far so good. And what would this do in terms of the supremum? Well, so now I took a difference. So the difference is still is 1 over n times 2x plus 1 over n. I'm taking a supremum in x. Well, clearly 1 over n is a constant. 2x plus 1 over n is a linear function with a positive slope. So its supremum is its maximum actually on the interval from 0 to 10, including 0 and 10, is going to be its value at 10. But then the supremum, because it's a continuous function, 1 over n, 2x plus 1 over n, continuous function of x, then the supremum on an open interval from 0 to 10 must be the same as a maximum of this function on the interval, on a closed interval from 0 to 10. And so this is then nothing but 1 over n times 2 times 10, plus 1 over n. So 1 over n times 20 plus 1 over n. And what happens to this when n goes to infinity? 20 plus 1 over n is no larger than 21. I take a number 21 divided by n when n goes to infinity. This goes to 0. So again, by either a squeeze theorem or by properties of limits, I can immediately conclude that this goes to 0 as n goes to infinity. And then what is the conclusion here? Well, the distance between fn and f goes to 0, so the conclusion is that fn converges to f uniformly. All right, next one is example number C, n times x to the power n, and x is from 0 to 1. Okay, so C, pointwise convergence. What do we do here? Actually, before I talk about this example, let me mention one thing. So by now we have two things that can happen uniformly. We can have a sequence of functions that converges to a limiting function uniformly, and we also have uniform continuity. Now these two things, besides the word uniform, are completely different. Because what does uniform continuity do? Uniform continuity refers to a single function being continuous on an interval, right? And uniform continuity means that somehow the rate at which this function is changing is limited, is bounded, right? It's bounded on the entire interval. Uniform convergence deals with sequences of functions, right? So you have infinitely many functions. And when we say uniform, we just mean that functions fn get uniformly close to some limiting function f. So uniformly means at all x at the same time. So in both cases, we're talking about something that happens for all x at the same time, except that the thing that happens is totally different. In one case, uniformly continuous function is sort of equally continuous at all points, in the sense that in the epsilon delta definition, again, delta is independent of epsilon. It can be chosen independent of x. And in this case, function is going to get, function fn is going to get close to function f also at all x. So something happens at all x in both cases, but again, the thing that happens is totally different. So please don't confuse these notions. Okay, so pointwise convergence, I'm going to fix any x in the domain. So domain is between 0 and 1. And consider the limit of a sequence of numbers, limit as n goes to infinity, n x to the power n. Okay, so x is a number between 0 and 1. If I look at this limit, then what exactly do I see? I see that n goes to infinity. X is a number between 0 and 1. If I raise it to larger and larger power, x to the power n is going to get smaller and smaller. So this is nothing but the indeterminate form, the product of something that goes to infinity. This is n. And something that goes to 0, and that is x to the power n. How are we going to deal with a limit like this? For an indeterminate form, I have to, in this case, probably use L'Hopital's rule. Let's try to do that. So L'Hopital's rule, even though we have not proved it yet, but we will at some point in the future. So what do? First, we rewrite your limit in a form, something that goes to infinity over something goes to infinity, or something goes to 0 over something that goes to 0. So in this case, I can keep n in the numerator, and I can divide by x to the power minus n, right? That really changes nothing. I simply rewrote my expression in a different way. Now, x to the n was going to 0, so x to the power minus n should go to infinity, and n goes to infinity. So this is infinity over infinity. N here is a discrete quantity. So if I want to use L'Hopital's rule, I would need to take a derivative with respect to something. So I will replace n by t, where t is a continuous quantity now, continuous variable. Clearly, if the limit in t exists, then the limit in n is going to exist as well. So this is a limit of t over x to the power minus t. And then L'Hopital's rule tells me that I can take derivatives of top and the bottom. On the top, derivative is 1. And then derivative with respect to t of x to the power minus t is going to be, if you remember, natural log of the base times exactly the same function as what you had in the beginning. And so now, if x is a fixed number between 0 and 1, and t goes to infinity, then I have x to the minus t. Before it was going to infinity. Now it still goes to infinity. 1 over ln of x is a constant, so this limit must be 0, right? 1 over infinity is 0. In other words, when I have a power of x, then typically power of x will converge to where it is going faster than just x to some power is going to converge somewhere faster than the power itself. So x to the power n, the thing that goes to 0, is going to beat n, the guy that goes to infinity. So doesn't matter, the limit now is equal to 0. So that means it's equal to 0 no matter what x between 0 and 1 is. So therefore, f n converges to f identically equal to 0, right? 3 lines just mean that f is equal to 0 for all x. So on pointwise, right, because we proved it for each individual point, for all points, because x was chosen arbitrarily. So pointwise on 0, 1. So the next question again is this convergence uniform. So what is the distance between Fn and f? Again, this is a supremum. X between 0 and 1, right? X is in your domain. And then Fn of x minus f of x, absolute value. Here it is a supremum x in 0, 1, and x to the power n minus 0. So supremum x between 0 and 1 and x to the n. So now, what is the supremum of this when x is between 0 and 1, right? I'm computing the distance between function fn with a fixed n, right, with a fixed index, and a function f of x. So that means that n is fixed. So what is my function n x to the n? N x to the n is a power function which is continuous for all x, right? So it does have a maximum on the interval from 0 to 1, on the interval that includes 1, right? Because x to the n is monotone increasing in x. Its maximum is at 1. It is continuous. So therefore, supremum of n x to the n on the interval from 0 to 1 must be equal to the value of that function at x equal to 1. So this supremum, then, if you should convince yourself that this is true if this is not clear, this supremum is just equal to n, right? And so now what happens to n as n goes to infinity? This, of course, goes to infinity. As n goes to infinity. And so then the conclusion doesn't go to 0, the distance doesn't go to 0. So that means that the convergence is not uniform. Okay? Okay, so basically, actually one thing that I would suggest you do, I'm not going to do it here, but try to sketch graphs of n x to the power n for different values of n, and try to convince yourself that indeed what we're saying here actually is true. Okay, so copy this, and let's talk about a different interval. And the different interval was from 0 to 1/2. So 1/2. Okay, once again, interval from 0 to 1/2 sits inside the interval from 0 to 1. I had pointwise convergence inside 0, 1 to the function 0. So that means that inside the smaller interval, I still have to retain the same pointwise convergence. And the same question as before applies: is this convergence going to be uniform or not? So now supremum is taken of the interval from 0 to 1/2 in all of these. And it's an immediate thing to see, right? Using the same ideas that I used so far. Function x to the power n is monotone increasing, and its maximum is at 1/2 on the interval from 0 to 1/2. So this function is continuous, therefore the supremum is going to be n times 1/2 to the n. But we already did this in a previous example. What is the limit of n times 1/2 to the power n when n goes to infinity? N goes to infinity, 1/2 to the n goes to 0. And I guess this is the same limit as I was considering here, but it's taken for x equal to 1/2. And I already know that that limit is going to go to 0 as n goes to infinity. And so on the interval from 0 to 1/2, convergence actually is uniform, right? So whether or not convergence is uniform will depend on just on the fact, it will depend generally on the interval on which you're considering your function. Depends on the domain. Okay, and so now we're ready to establish a few theorems about these things. And theorem number 1 will be this. The sequence Fn converges to F uniformly on the interval I if and only if for every epsilon greater than 0 there exists a capital N in R such that Fn of x minus f of x absolute value, that this is going to be less than epsilon if n is bigger than capital N for all x in I. Right, so basically what are we saying? We're saying that the convergence of Fn to F is going to be uniform as long as whenever I choose some epsilon greater than 0, then the difference between values of Fn of x and f of x is going to be always less than epsilon regarding of x as long as n is bigger than capital N. That's a thing that we were discussing before, that the uniform convergence means that the graph of Fn becomes close to the graph of f at all points at once, right? That's basically what this says, that Fn of x minus f of x must be equal to less than epsilon for all x. Proof? Let's do it in a forward direction first. So suppose Fn goes to f uniformly on I. So then what does that mean? The way we defined it, then the distance from Fn to f should go to 0 as n goes to infinity. So then supremum, I'm going to write it like this, then the limit as n goes to infinity of the supremum x and I of Fn of x minus f of x, this must be equal to 0, right? Okay, what does that mean? That means that for any epsilon greater than 0, by definition of a limit, there exists a capital N in R such that n bigger than capital N would imply what? It would imply that the absolute value of the thing, the limit of which I'm taken, minus a limit, that this should be less than epsilon, right? But if I'm subtracting 0, then really I'm not doing anything. And if I'm taking absolute value of the supremum, of absolute value of something, that also is greater than 0. So really, I don't need to take absolute value. But let's write this anyhow. So absolute value of supremum x and I Fn of x minus f of x minus 0. This is less than epsilon, right? This is equivalent to saying, so if n is bigger than capital N, this should imply drop 0, drop absolute value, just supremum x in I fn of x minus f of x. This is less than epsilon, right? And this is equivalent to saying the following. So if the supremum of some numbers is less than epsilon, that means that this number is less than epsilon for all x, right? So therefore, n greater than capital N should actually imply fn of x minus f of x is less than epsilon for all x in I, right? Because if the upper bound is less than epsilon, then each individual number is less than epsilon. Well, but that's exactly what I was trying to show, right? Because I was trying to show that for every epsilon there exists a capital N, such that n bigger than capital N implies fn of x minus f of x is less than epsilon for all x. Well, that's what I got, right? So that's proved. This part is proved, so now let's go in the opposite direction. Let's suppose let's just copy this. Okay, now that I finished with beautification, let's think what we're going to do. So let's suppose that for every epsilon there exists an n such that all of this is true. Well, so okay, so if the statement is true for all x in I, right? If for all x in I, fn of x minus f of x is less than epsilon, and then if I take supremum in x, then what should be true? If all these numbers are less than epsilon, then that means that the supremum is less than epsilon as well, but it can also be, in principle, equal to epsilon, right? And I want to avoid the equality sign, so then I'm going to modify things a little bit. So I can rewrite this, and this is purely a formal thing. It doesn't really affect the result. In a sense, it's already obvious that the result must be true. Again, if absolute value of fn of x minus f of x can be made less than a prescribed number for all x if n is bigger than capital N, then supremum of the difference between these numbers is going to be supremum of a difference between fn of x and f of x is still going to be small when n is bigger than capital N, right? So, and that has a definition of uniform convergence. But just to make sure that I don't get the equality sign, so let's just make the following observation. So then, if this is true, there exists an n in R, right? As epsilon can choose anything. So I'm going to choose capital N in such a way so that absolute value of fn of x minus f of x, so that this is less than 0.9 epsilon, right? I can always choose my capital N like that if n is bigger than capital N for all x in I. So then from this I can deduce now, if n is bigger than capital N, and I take the supremum over x in I of fn of x minus f of x, right? If everybody is less than 0.9 epsilon, that this supremum must be less or equal than 0.9 epsilon, right? But if it's less or equal than 0.9 epsilon, then must be less than epsilon. Okay, so then what have we got? If I choose epsilon greater than 0, there exists a capital N in R, such that if n is bigger than capital N, then this guy is less than epsilon. But this guy being less than epsilon means that this supremum of fn of x minus f of x, that this goes to 0. And so therefore, the limit n goes to infinity of the supremum x in I fn of x minus f of x, this is equal to 0, and therefore fn converges to f uniformly. So this theorem then allows me to define a uniform convergence in two different ways, either via this epsilon n definition or just via the supremum definition. And depending on what we're going to do, one is going to be easier to use than another. So both will be useful. And in fact, I'm going to use this immediately to prove the following theorem. Suppose that fn converges to f uniformly on I. Then fn converges to f pointwise on I. Right, so convergence, uniform convergence is stronger than the pointwise convergence. And we already saw examples where the sequence would converge pointwise but not converge uniformly. So this says that if a sequence converges uniformly to a limit, it must converge pointwise to exactly the same limit. And the proof is going to be really simple. So the proof, suppose, let me just make a note here. So note that the reverse of this is not true. Just make sure that you remember this. So suppose fn goes to f uniformly on I, then for any epsilon there exists a capital N such that n bigger than capital N would imply that fn of x minus f of x is less than epsilon, and this is for any x and I, right? That's our uniform convergence. So then, if I fix any x and I, right, then what do I know? If n is bigger than capital N, I'll have that fn of x minus f of x is less than epsilon, right? Because it was true for any x here. All right, but then what does it mean? It means that for any epsilon greater than 0, maybe we should add that here. For any epsilon greater than 0, there exists a capital N such that, what happens? Such that if n is bigger than capital N, fn of x minus f of x is less than epsilon. What is that? That's a definition of a limit. So limit n goes to infinity of fn of x is equal to f of x. And so therefore fn goes to f pointwise, because this should be true for every x in I, right? So again, I use the previous theorem on the first step here, right? If fn goes to f uniformly, then epsilon definition of the uniform continuity, uniform convergence applies, right? So for any epsilon, there exists a capital N such that this is less than epsilon for any x, as long as n is bigger than capital N. And so then for a fixed x, the same thing is going to be true, and that means that the limit exists, and therefore exists for every x, and therefore I have my pointwise convergence. So if I can prove that the sequence of functions converges uniformly, then I don't need to do anything for pointwise convergence, because that is going to be automatic. Okay, and the last theorem for this lecture is going to be this. They're going to be the following. Suppose fn is continuous on I for all indices n and n, and fn converge to f uniformly on I. Remember, we're talking about the criteria that we wanted to find on convergence of a sequence of functions to guarantee that the sequence of functions that are continuous will converge to a continuous function in a limit. And that's exactly what this is. So if I have all functions are continuous on I, and all functions in my sequence are continuous on I, and if a sequence converges to its limit uniformly on I, then f, the limit, is going to be continuous on I. So we are going to prove that right now. And maybe I will do I'll draw a small picture first. So what have we got? We got a sequence of functions on some, let's say, interval from A to B. I'm not going to sketch the entire sequence because there are infinitely many functions like that. But I just know that there is some limiting function. And because convergence is uniform, I also know, so if this is my limit f of x, if convergence is uniform, then I know that functions fn are going to be uniformly close to f of x. So for large n, fn may look something like this, right? It is supposed to get arbitrarily close to f of x. If I want to prove continuity of f of x, how can I do that? So continuity at the point x means what? It means that I want to be able to find, we have to use maybe epsilon delta definition or continuity. For f dx, I should be able to find, in f d epsilon, I should be able to find the neighborhood of x within which the difference between the value of the function at x, in fact, let's call it x0, I'm going to fix x0, at x0 and nearby points, that the difference is going to be less than epsilon. And the way I'm going to do it, so I want to compare values of the function f at x0 and so f of x0 and f of x, I'm exaggerating here a little bit, at some nearby point. So this value and that value. How can I compare them? I can try to do this. I can take a step down from a black graph to the red graph. Red graph is a continuous function, so I know that if I want the y values, the difference between y values of the red points to be less than epsilon, there exists a delta such that if x minus x0 is less than delta, then fn of x minus fn of x0 is going to be less than a prescribed number. So a difference between y values of red points I control, and then the difference between black points and red points I also control, because fn minus f is supposed to become as small as I wish. And so then the difference between y values of two black points I can estimate by these differences between black and red, and also difference between two red points. All of those are small, so hopefully the difference between y values of two black points is going to be small as well. So there will be three changes that are involved here, right? If I want to find change between f of x and f of x0, I have to estimate this number, difference between red, and then another black and red. So that means that I'll have to estimate three quantities. And because I need to estimate three quantities, and at the end of the day, the sum of these quantities will control the difference between values of f of x at 2 points, and I want to make all of these quantities to be less than a third of epsilon. Okay, so let's now write this down. Given an epsilon greater than 0, there exists an n in R such that the supremum when x is between a and b, or in I, because I assumed in the beginning that my point belongs to the interval I. So the supremum of fn of x minus f of x can be made less than epsilon over 3, right? So I can do this because fn goes to f uniformly, right? So that is just a fact of life. Okay, so now I'm going to choose any fn, any function fn with the index n bigger than capital N, right? I'm also going to choose an arbitrary x 0 in I, right? And we want to show that f is continuous at this point x0. Right? So if we can do that, then we're done. Because if x0 is an arbitrary point in I, then that means that the function is continuous everywhere in I. Okay, so what am I going to do? I'm going to then say the following. Because Fn is continuous at x0, right, by our assumption, there exists a delta greater than 0 such that Fn of x minus Fn of x0 is going to be less than epsilon over 3 if x minus x0 is less than delta, right? This is just a definition of continuity of a function Fn. And the only thing, the special thing that I'm doing here, sorry, I'm choosing my epsilon to be actually epsilon over 3. Which I can do because I can put any number on the right-hand side of this inequality. Okay, so now let x minus x0 to be less than delta. And then I want to estimate the difference between f of x and f of x0. And I said that I'm going to try to accomplish this by estimating these differences between red, black points, etc. So I'm going to use the following argument. So f of x minus f of x0 I can write as f of x minus fn of x, right? I'm subtracting fn. There is no fn in the regional difference. So to get rid of it, I can add fn of x. Then, for some reason, I'm going to subtract fn of x0. There is no fn of x0 in the original expression here, right? So to get rid of it, I will need to add fn of x0. And there is minus f of x0 that I have not accounted for yet. Well, so now I can group these things together. First two, second two, and the last two. Well, then I have a sum of absolute value of a sum of three numbers. So triangle inequality says that this should be less or equal than absolute value of fn of x minus f of x plus absolute value of fn of x minus fn of x0, and then plus absolute value of fn of x0 minus f of x0. And actually, I know quite a bit about these individual numbers. First of all, I know that the function fn of x minus f of x, because n was chosen to be bigger than capital N, right? Fn of x minus f of x is less than epsilon over 3, because the supremum of fn of x minus f of x is less than epsilon over 3, so then this guy, the first guy here, is less than epsilon over 3. And actually, the last guy is exactly the same thing, right? Because the difference between Fn and f at a different point at x0, but the supremum of the difference between Fn and f is less than epsilon over 3, so the last thing is also less than epsilon over 3. But now what did I assume about x minus x0? I assume that that is less than delta. And because it is less than delta, then Fn of x minus Fn of x0 is also less than epsilon over 3. So the middle term is less than epsilon over 3. So we have 3 epsilon over 3's, which is epsilon. So what have I found? For every epsilon, there exists a capital delta, right, that comes from continuity of Fn, such that if x minus x0 is less than delta, then this thing, this difference, is less than epsilon. Well, that doesn't mean. It means that my function f is continuous at x0, right? So f is continuous at x0 because the definition of continuity, I mean, equivalent definition, epsilon delta definition of continuity, is now satisfied. And the last thing that I want to do in this lecture is a quick example. And a quick example will go like this. Let's go back to one of the original examples that I considered last time. So let's take Fn of x equal to x to the n, and the interval is going to be between 0 and 1, let's say including 0 and 1. What I want to do is I want to find the pointwise limit of Fn of x, or just of the sequence Fn. And I also want to determine whether the convergence is uniform. Okay, so last time we found that Fn converges to f pointwise, where f was equal to 0 if x is between 0 and 1, not including 1, and 1 if x is equal to 1. So now, x to the n, so first of all, the way we proved that the sequence does not converge uniformly last time was that we found the supremum of the difference between Fn and f, and it turned out that this difference did not go to 0. The supremum of the difference did not go to 0, so the convergence is not uniform. How can I see that it's not uniform here without doing these computations? Well, I know that Fn is continuous, right, because it's x to the n for all n in n, but f is not continuous at 1. Well, can the convergence be uniform? No, because if it were, then the limit would be continuous, and it's not, right? So from the theorem that we just proved, this convergence is not uniform. And we'll continue with this next time.